So we are into the fourth lecture of second week, and we will be discussing some machine learning techniques or statistical techniques in this lecture um, that gets integrated with the artificial intelligence or ANN model to give the desired results. So we have this techniques, that is ANN supervised learning, and support vector machine we have discussed. Support vector machine is a unsupervised learning actually. Let's say regression, it's a very important tool actually, because we make sometimes a assumption for a model. We do not know how a physical entity is representing our data, and this is a technique which gives us insight into that. Then we have genetic algorithm, okay, gradient descent method, KNN, and reinforced learning. This is called K nearest neighbor, KNN. So let us see regression. I'll explain this whole technique into by having a validating the assumption or ascertaining how our data is being represented, whether they are adequate enough to be represented by a line and all that. So this is a regression technique we have here. Let us say in a typical life test, you collected data. Probably you all may not be knowing, like normal distribution, exponential distribution. There is called Weibull distribution, okay, and you know that normal distribution is a bell-shaped curve, okay. Exponential distribution is a curve, non-linear curve, and then we have this Weibull distribution. So Weibull distribution is, in reliability parlance or engineering, is used to plot the live test data, okay. So I am showing you some data has been collected, and the data point 1, data point 2, and we have gone up to data point 10. In between data points are there, and we have plotted a we thought that let us represent this data by this line, because you see they are around this line actually, but I am not sure how well this data can be represented by this line, okay. It's a big question. It is my assumption that this line is being represented by this data. Now what to do? What is my confidence? So this is a regression technique, and in PHM it is required, because I have to always represent a line, whether my data is having a normal distribution, whether my data is having a Weibull. Actually, Weibull distribution is good, because if the data is basically belongs to an exponential distribution, then the line that is there, this line will have a gradient tan theta, you can say, no, gradient will be 1, that is perpendicular base, you know. So this will be 1, okay. So so that means beta is equal to y by x. If it is around 1, it is an exponential distribution. Isn't it beautiful to get idea from the data about a distribution? Now 1.1, maybe we can check it for normal distribution also, whether this data is following. So that means when I plot this data on a exponential probability plot, they will be almost falling in line. It is that. So why people use exponential distribution is because suppose if the line shows a gradient, the gradient is nothing but the slope parameter of the line, okay. So so if suppose beta comes to tan theta comes to, let us say, 3, that is slope of the line. it is giving an idea that it is a normal distribution, and so on and so forth, you know. So that means one distribution is giving me idea about many other distributions, you know. So that's why beta is a very, beta means this parameter of the Weibull distribution. There are two parameters in Weibull distribution, alpha and beta. Alpha basically talks about the characteristic life. When you plot, when you drop a line from 63.2 that thing, and you drop it here, it will give me characteristic life. So alpha gives that value, so it is called characteristic life. And then beta means the slope of the line. Okay, if the slope is here, definitely it will not be 1. Y by x ratio will not be a 1. So so it will be some other distribution. Okay. Now this is a graphical representation, and we have, with the coefficient of correlation, we will know. Now this is a we are trying to, R is nothing but coefficient of correlation. So there is a formula, which statistical formula, which gives summation of x, x bar, y bar, and all that. And then we have this I is equal to, so because we had 10 data points, so our I was 10, and then x value and y values were there in the table, and then we have got this. And if the coefficient of correlation R is more than 0.9, then you have a quantitative confirmation that the data is represented by this line, it is in conformity. Okay. If it is 0.95, very good, but minimum should be 9. If it is below 9, that means they are not agreeing this. So one is that you had data plotted on the Weibull plot, drew a line, and then we had this how well the line is represented. We have done a regression analysis here, and we could confirm that actually. Okay. So here I am talking about beta is equal to 1, exponential delta, beta is equal to 3.0, and then there are two parameter in Weibull distribution, that is characteristic life alpha, and beta is the slope. Actually it can have 3 parameter, theta, that means where from it is starting. Okay. If suppose sometimes the distribution might start from there, so that will be starting point. So theta, but normally we talk about 2 parameter distribution. Okay. And it's very useful, and this type of knowledge in AI, it does wonder actually, because if you are looking for a linear relationship, you have something here. Okay, who is coming close to the, which properties are coming close, which are going away, and things like that, you know. Now one more tool is there, genetic algorithm. Genetic algorithm is basically an inspiration from how genetics are evolved in our biological body actually. So the chart is like this. We have first we have this we have to start and initialize a population, that we are talking about. But if we take these 3, natural way of is natural selection, crossover, and mutation, they are basically in biological properties. That is how the offspring, they are born and they bear some characteristic from the parents. So it is between parents, child, and this technique is so useful in optimization. If we have an optimization problem where the simplex techniques in optimization, it works when the things are linear, or when there are only one optimum point, maximum or minimum. But if there are, while going for optimization, there are so many in the given space, there are so many maxima and minima, which one is the best? So that is where this genetic algorithm, it works. And why it works and it does produce better results? Because its power is random selection, which can be there anywhere in the space. So that means the chances of localized solution is eliminated. So a genetic algorithm comprises of looking a solution in the optimum solution in the space. It comprises 4 steps: random initialization, okay. Then so we have done the initialization, the global search space in place of a localized initiation. So it takes all the whole population or whole space to optimize. Why? Because we want it not to get a localized solution, which will be misleading actually for any solution when we go for optimization. So, and about to eliminate the possibility of local minima. Simple example, I am training my artificial neural network, okay, and then while training, it gets into, because of momentum, you know that ANN works on training coefficient and momentum coefficient. You have to, these are the parameters you have to select while training. Sometimes the current machine, they select on their own looking at the problem, but sometimes it was required that we have to do a parametric study and find out the best solution. So while training, if the convergence got into local minima, it will not come out of the minima. But suppose if we do using this optimization through a genetic algorithm, the local minima can be avoided easily, because it goes to another random point and see what happens actually, and you come out it, you know. This leads to a global solution. The best way to characterize genetic algorithm is it gives a global solution. The 3 processes involved in this thing are mutation, crossover, as I said, and like we have in genotypes, towards more accurate prediction compared to traditional approaches in linear optimization. Testing and validation should be found to rule out the overfitting. Sometimes there is a like, suppose if they set the parameter, and if the parameters are set very close, it will be computationally expensive. But if we keep it too off, then it will be shunting between up and down. I'll show you through the figures and all how it happens. So, so choosing a parameter, even if it is an auto, it is very important. So let us go to the next slide. Some characteristic of gradient optimization, and they are shared. Only difference is gradient optimization, it works on the slope, okay. In line with the linear optimization, the gradient optimization algorithm for optimize for first order and second method and objective is to find minimum of the function. See the figure, okay. Gradient is a vector given characterized by fx. Each element in the slope of the parameter function along with the direction of the one of the variables. As also each element is a partial derivative. You can say here we have each element x0, x1, they are partial derivative, and this is a vector being defined. And the equation, this, if we consider this equation and apply on this second derivative and all that, you will find for this equation you have this solution. So what it comprises? The procedure steps in choose a starting point x0. Okay. So this figure I am showing for illustration actually. So you can start anywhere and determine descent direction. So if there is a descent direction, that means the gradient should be 0. If you are reached optimum, either maxima or minima. So we have, these are the A, B, C, they are the maxima, and D, E is the minima over here. And accordingly choose the learning rate, update the positions, okay. So it is weight plus n delta t, like it happens in artificial neural network, and go to the next step. Step 5, repeat from 2 to 5 again. If you, so learning steps too small. If they are too small, the convergence means arriving at the solution. It takes lot of time actually. And if the learning rate is too large, then it can shift from here to here, here to here, and it will keep moving in this only. This will assure you that it is going to the minima, but it requires a lot of, so there has to be optimum value of learning rate and training rate in neural network also. So when we design your own neural network, you have to be very Even if it is selected by the system, you have to see that they are not too small, they are not too big. Otherwise, you see, here it got trapped into local minima, as I was discussing you in the previous slide. So, and it will not come out. It will go on hunting from this to this to this and all. So, training will not be completed. It will stop. So, you have to give a momentum, increase the momentum and bring it out of this loop, and further training will go on. Okay. So, that is possible when manual intervention is permitted. So, gradient descent method. K nearest neighbor is very elegant method for creating clusters. The K nearest neighbor, KNN, is generally referred as, is a non-parametric. If you ask me what is the parametric and non-parametric, parametrics that can be defined by a function, normal distribution, Gaussian distribution, they are all parametric. But non-parametric, which cannot be described by a distribution or a formula. And it is a supervised learning classifier. You have to give a solution. Somewhere you have to give some hint to the data, these are the category or what, which uses proximity. So, to make classification, proximity means distance between, eliciting distance between 2 points. Okay. So, this is our target point. Okay. Suppose if I give this as a target, so things are K3 are clustering around this, and we have got this point actually. Now, KNN is one of the popular and simplest classification and regression classified use. Don't you think it is, once we give the target vector and input vector, then my target point is here. Okay, it could be somewhere also, and then it identifies the cluster. Okay, it builds a cluster around that, and we are able to analyze the data. And of course, it is supervised learning. The class of value of the data point is then determined by majority voting. Majority vote means suppose out of 3 points, if 2 points are telling the same thing, it is majority voting. So, majority voting means out of 3 points, all the points are the 3 out of 3 or 2 out of 3. Okay? 1 out of 3 will not be majority voting. So, that kind of things are used to characterize the target. Evaluation of distance, it is called elicited distance, nothing great, it is a physical distance in a space actually. Between 2 points is integral to the KNN approach model. Elicitation, or even it is called Cartesian distance. This involves evaluation of the Cartesian distance between the 2 points. So, we have to evolve this distance and all, and how it is done? It is done by variable x and given characteristic x target, we have x minus xj, and then j is equal to 1 to d. Okay. So, we have defined elicitation distance typically like a definition, elicitation space, the length of the straight line segment that would connect to. Sometimes the jargons confuse you a lot, so the definition has been given, and the source of this particular slide or presentation is this one. 1 or 2 sources I have used for K nearest neighbor point. And then reinforced learning. It's a very powerful technique, because we have on one side we have supervised learning, unsupervised learning, and the third category is reinforced learning. And here there are 3 elements, and these elements are agent, environment, and reward. It's a elegant picture to demonstrate what is the thing. So, you have agent, you have environment, and you have action, which will be reflected in the figure here. Okay. So, how it works? Experience or the past data basis of learning. Whatever you have data and all that. So, that means it is sort of going towards past data for reinforcement to be learned. The agents operates in the 3 major steps in the basis of action agent. What is the basis? What is the basis for any action? That should be, motivation should be known, and then reward. What reward you get? For that reward, you will be taking a action. Environment evaluates the action and provides feedback in the form of a reward. The reward signal reflects the performance of the reaching goal. So, these are the basic elements of this algorithm, and then model based and model free learning. So when you have a model, you can get the results. So now just to describe your environment, or let us understand with this figure, there is a dog sitting here. His action is to move and walk, and he will move in the direction of reward, whatever is there actually. So this is what it is. So these are the things we have studied.